Okay, hello everyone. My name is Dikopoltsev. I'm from Moti Segev's group, and my talk is about topological insulator lasers. It's related to quantum simulators. I will start with the most interesting features of topological insulators. They're insulating in the bulk. You can see the band structure of the bulk. It is gapped, and they're conducting on the edge. They have some supercurrent on the edge that is scatter-free, and if you have disorder and defects, it overcomes them. And you can see this also by having the modes that support this conductance lie exactly in the topological gap. And the size of the gap is what defines the protection. As the gap is larger, then the protection is better. And the most common example, the first example, is the quantum Hall effect, when you have magnetic field at very low temperatures and you can have this supercurrent on the edge. Also, the modes lie on this dispersion curve that is tilted. So you can see it has non-zero group velocity. And this is also one of the reasons that you have this current of energy around the edges. Okay, so this idea was implemented in photonics. In many systems, we were the first group to demonstrate it experimentally using twisted waveguides when light propagated in a certain direction. And we emulated a Floquet topological insulator. And while many groups pursued solid-state models to emulate these topological Hermitian systems, so we went to a different direction, a more bold direction, because you don't have any analogy in solid-state for this, to non-Hermitian topological insulators and nonlinear topological insulators. So the strongest example that we have is the topological insulator laser. It demonstrates a new concept. Non-Hermitian topological insulators, it's a debatable subject. So when we started to work on these lasers, people didn't believe it can be possible. And we showed them otherwise. Also, can we have topological transport with gain, or when the system is highly nonlinear? So I will now explain our model. We have this this lattice that supports topological edge modes, and we add loss that is typical to lasers and saturable gain, okay, which is highly nonlinear. Now, this idea came out also to be a demonstration, a real-life demonstration. We combined many lasers in the lattice that had this topological protection, and the lasers on the edge of the lattice, the cavities, were lasing in a single mode, combined when the energy was transported along the edges of this array, and lased together coherently in a single mode. You can see the spectrum. This is a measured spectrum of this array. You can see that the topological spectrum is narrow, it is strong, and the trivial is pretty wide in this demonstration. So again, topological protection is the thing that allowed us to combine many lasers together to lock and act as one. Now, there was many follow-up for this work, experimental also in QCLs and electrical pumping, and also some theory work that showed that these lasers are indeed coherent. So this is good to use topological lattices for lasing. But all of this work had something in common. The light that propagated in the cavities in the waveguides was in the same plane where the coupling that led to this topological protection was. So you can see that the light propagated in plane all around the array in all previous works. And this requires an output coupler, because otherwise you cannot take the light out. So you put an output coupler, but this is a major defect. Think about a huge power plant that provides a lot of electricity, but you have one small socket, power socket. This can damage the devices. This can also this can cause high nonlinearities. And we suggested to do something that is conceptually different, to have the light propagating vertically up and down, for example, and the coupling will be in a different plane, in plane. And for this, we used cavities, and specifically VCSELs, which are vertical cavity surface emitting lasers. And they're very common. You have it in your computer mouse, you have it in your Face ID apps, and in telecom, and many, many other applications. But they have one main disadvantage. They're small, and therefore they're limited by their power. And there was the idea to couple these lasers into using like a large array, 2D array, to couple them evanescently, and hope that there will be like one mode over the whole array that will laze coherently together. but the problem is that inevitable imperfections and defects in the system would cause localized modes to appear, lays independently in different frequencies, and therefore the device will be incoherent. And also, worse, as the array size grows, the coherence will be decreased even more. Now, we suggested to use topological protection to combine these VCSELs together into one coherent laser-locked device. And from all these photonic topological insulator models, we decided to go with a crystalline model, which is geometric, based on geometry. It is based on a honeycomb lattice with two sub-lattices. One is compressed and one is stretched. And in between, you will get this nice topological mode, where each site here will be a VCSEL. Now, we use the same model from before. This is just for the modeling. And we pumped the topological edge to look for topological lasing. And this is a simulation. We start with a completely random seed and random amplitude, like happens in lasers. And the left is the amplitude. You can see it converges to the topological mode. This is a continuous wave simulation, by the way. And the phase acts really nicely. It has like this 2 pi wraparound. And this is because in this kind of systems, there is a spin momentum locking, for those who know. And this allows for this protected lasing of the topological modes. Now, we went and fabricated this device. This was a collaboration with the Würzburg University. And this, you can see a wafer. The top and the bottom are Bragg mirrors. And in the center, the red line is the cavity with the gay medium. And we etched the shape of the crystalline, okay, the geometry of the crystalline. And we measured what we got. So first, photoluminescence measurement. Before we get lasing, we just pump it a little bit. And we measure the bulks. The bulk is gapped. As we talked, the bulk should be gapped. The black line is our model. The second bulk, also the stretch, is gapped. But when we illuminate the center where we have the topological interface, we see these topological modes appear exactly in the topological band gap. And also you can see the black line, it sits exactly where we predict them to be. So what we do next? Now we pump it to lasing. Okay, so we used an SLM and shaped this beam and pump the topological edge. And the result is what you can see here. Left is the near field lasing of the device, and the right, the spectrum of the laser. And the solid red line is the spectrum of 30 VCSELs. The green line is the spectrum of a single VCSEL. So you can see how similar it is. That means that 30 VCSELs act very similarly to one VCSEL. Now, moreover, this frequency lies exactly in the topological band gap. That means that this is actually topological, lasing in topological modes. Now, does it mean that all the VCSELs inside the array are coherent? No. Okay, you can have two different lasers with the same spectra, but they can be completely not coherent between themselves, between each other. So what we did an interference measurement. We imaged the near field of this laser array with its mirror image, one on top of the other, with a slight tilt. And when we have two lasers that are coherent, we will get interference fringes. When they are not coherent, we will not get them. But here we did get it. So specifically, let's look at the symmetry axis. This point means that this is the autocorrelation of a VCSEL with itself, the interference of a VCSEL with itself. This is not surprising that we'd see interference, right? Because a laser is coherent with itself. But when, it's okay. But when you look at these two green circles that are separated 13 VCSELs away and 3 corners apart, then you can still see these fringes. That means that they're still coherent between each other. And we can take the modulation amplitude, just draw it aside, and we see that it's pretty uniform. And just to emphasize how topology helps us, we can compare it to the trivial case. This is what we did in an experiment. Again, this is an experiment. And you see that the coherence is uniform along the topological array, but in the trivial array, it's centered only around the symmetry axis, which means that it's mainly autocorrelation, and there's much less coherence between two separate VCSELs that are far apart. You can see how the coherence is degraded. This is the integration to the right. So we have much more ideas and much more work to do in this field of topological photonics. This is just a small part of it. I want to thank the team, the Moti, and everyone. Thank you.